Right now, if you remember the last week, we talked about the radiation and spectra, and we discussed about the electromagnetic spectrum and how uh, different parts of the electromagnetic spectrum is how properties of the different part of electromagnetic spectrum and how why it is important for us when we are learning astronomy, right? And we discussed that there are different wavelengths have different properties, and some of them may will penetrate through the atmosphere and will reach to Earth. For example, the visible light, but there are certain wavelengths like such as X-ray and gamma rays that they never reach to our Earth. Because of that, when we make telescopes to detect X-rays and gamma ray kind of thing, then you have to go to the space, right? So that's how it works. Now, keep in that mind. Now, this today's session we will talk about astronomical instruments. So last time we talked about different properties of electromagnetic spectrum, but I mean, to do all these observations and finding new things, we need some instruments, right? Now, the aim of this particular lesson is to discuss and make you aware, and also just to get a basic understanding what kind of instruments that we are using in astronomy, and also we will try to understand like basic mechanisms, how these things work, right? So that is the aim of this particular lecture. Right now, to start with, I hope all of you know this particular image, and this is the image of the Hubble Space Telescope. Probably we consider this particular instrument as kind of the most, I would say, most valuable instrument for astronomers for the past, like, let's say 3 decades, from starting from 1990s up to 2010, 2015. And you will probably know that it is not the case now, because we have sent more advanced and completely new space telescope very recently, which we called as the James Webb Space Telescope. This is launched around like 6 months ago, around last December. I think the first image of the James Webb Space Telescope reached to us few days ago, as far as I remember. So, and you may have a question now why we are actually even building these new telescopes, right? So you had this Hubble Space Telescope. Why do you need another one? Right? So these cost a huge amount of money, right? So the aim of this lesson is also to show you why these instruments are important in astronomy, right? And this is Hubble Space Telescope. Right now, if you go outside and look at the sky, in reality, there are about 9,000 stars visible to the unaided eye. So unaided eye means we don't use any kind of instruments, and if you just look at the outside, you will see around 9,000 stars in both hemispheres, right? In both southern and northern hemispheres. Now, the problem is, how can we learn about the vast majority of objects in the universe that our unaided eye simply cannot see? Now, this is only what we can see, right? So we can probably get some idea about the things that we can see, but most of the objects in the universe we cannot see from our unaided eye, because the eye is not powerful enough, right? And now this is where we need some instruments. And right now, different explorations of space. Now, almost everything that we know about the universe came from studying electromagnetic radiation. So that's what we discussed in the last chapter. And exploration of space in 20th century made it possible to detect electromagnetic radiations at all wavelengths, from gamma rays to radio waves. So we know that from the explorations that we have done, we can detect all kind of wavelengths from space, right? Now, these different wavelengths carry different kinds of information, right? So that's what we have discussed in the previous chapter as well. Now, what kind of information these kind of different wavelengths can give us? So one is that the appearance of any object, that often depends on the wavelength that which we use to observe. For example, if there is a particular object that emit only X-rays, and if you are looking at this particular object from a large optical telescope, you will never even detect that particular object, right? Because it doesn't emit any visible light. It only emits powerful X-rays. So if you want to detect that particular object, then you have to use an X-ray telescope, right? So that's how it works. Right. Now, not only the telescope is actually not the only instrument that we are using in astronomy, right? Now, if we want to measure some kind of radiation or certain electromagnetic wavelength or a part of a wavelength, there are basically three basic components that we use in a modern system for measuring something, right? Number one, of course, is the telescope. Now, the telescope serves as a bucket of collecting visible light, right? So that means the telescope is the primary instrument that we have for us, and we will use that to collect light. So the purpose of a telescope is just to collect the light from a particular instrument, right? Now, this is why we need larger telescopes. So if you can build a larger telescope, then you can catch more and more light from a distance object. If the telescope is smaller, then the amount of light that you can catch from that telescope will be a small amount, right? So this is why astronomers used to build large telescopes by spending so much money, right? Because it will be very helpful to catch more and more light and look at the things that we have not seen before, right? And the other thing is, the second instrument that we need is an instrument that is attached to the telescope that sorts the incoming radiation by wavelength, right? So this is a different instrument that you have to attach to a telescope. Telescope, everybody knows, right? Normally, you know what a telescope means when I tell that. Now, the second instrument that we are going to attach to a telescope is a different one. That is actually to sort out this incoming radiation for different wavelengths, right? Now, for this one, you may not be familiar with this one. This includes basically two things. That is a spectrograph or a filter, right? A filter means that once you catch all this light to a telescope, let's say you need only to look at this particular object through red light. Red light means there is a wavelength range for the red wavelength. If you need to look at the particular object through red wavelength, then you are going to attach an instrument called the filter. So the filter filters out all the other wavelengths except that red wavelength, right? So there is a wavelength range for that. So this filter will filter out all the other wavelengths and will take the red wavelength only, and it will come to when you eyes so whatever the next instrument. The next instrument is actually a detector, right? So detector is any kind of device that sends the radiation in the wavelength regions that we have chosen. And then you should be able to permanently record the observations, right? Now, for example, our eye is a detector, right? It is a detector that you can detect all this light, right? But in here, what we are talking is a device, right? A detector which acts as a device. It can sense different radiation that coming from different wavelength regions and then can permanently record it, right? Now, anybody can answer what kind of an example for a detector? And you all know this, these detectors. Can any of you give an example for a detector? When in astronomy. I think one good example is a camera, right? So if you take a digital camera, it is a detector which can catch the light photons and record it, right? So it is a detector. Now in astronomy, the main detector is actually a camera, and most of the time this will be a CCD camera. We used to call this as charged coupled devices, right? Now, history of development of astronomical telescope is about how these new technologies that we have been applied to improve the efficiency of these three basic components: the telescope, wavelength sorting device, and the detectors. Now, the development of these astronomical observations and astronomical discoveries actually will be improving with the improvements of these new technologies, right? Normally, any technology that you are using today, most of the time they will be using for the first time in one of these high-end applications, such as in observing the universe or those kind of things. Now, uh, when we have the technology to develop larger and larger telescopes, then we can detect more light and have a more understanding or better understanding about the universe. Right? And at the same time, when we have, if you can make a good camera that is more sensitive to different wavelengths, then you will be able to record a lot of things that you didn't have the opportunity to do before, right? So that's how this works, right? Now, just to give you an example, here is the region of a universe, so region of a sky, which is the, just give me a minute, right? Yes. Right. This is a region of the sky, and if there is anybody who is a little bit familiar with the sky, you all know what is this region, right? So this is the region where you have the Orion constellation, right? And Orion Nebula is also here, and we will talk about what is a nebula in a later chapter when we are talking about the stars. Now this is there are three images right here, A, B, and C, which are basically from the same part of the sky, which is the Orion area where you have the Orion constellation. The only difference is this is observed from instruments that are sensitive to different band of the spectrum, right? So these objects are observed from three different bands of spectrum, right? Number one is the first one is using just visible light, right? So the first image, image A is how this area in the sky looks like when you observe it from visible light, right? Now these dotted lines right here are actually to show the figure of this Orion constellation, right? So these dotted lines are something not that you are observing, right? So this is like these hypothetical lines that shows you the Orion constellation, and here is the Orion belt, and this part right here is where you have the Orion nebula, right? Nebula is like a small nurseries for new stars, which is like a gas cloud. And actually, if you have a smaller telescope, you can, if you can focus it to this region, you can actually observe this Orion nebula in the dark in a time that where you have a dark sky. And on the same region, if you look through X-rays, in this part B is how it looks like the X-rays, right? So it views then you can see large number of things that you have you cannot see from this optical region, right? Large number of objects you can see. right? So those are objects that emit primarily X-rays, and because of that, uh, you cannot, observe those from your human eyes or through optical telescopes, right? However, just to keep in mind that these colors are actually some artificial colors, not actual colors. So those are actually show you the different energy levels that they are releasing in the X-ray region, right? Basically, we use blue for increasing energy, and for the other red color is will be like a decreasing energy, right? So if the energy is X-ray energy is higher, we have to have a blue color here. It's kind of color coded to show you different energy levels coming from X-ray, right? So what you can understand here is the same region when you look from an X-ray telescope, uh, it's completely different, right? You cannot see huge, large number of objects that you cannot see from the optical region, right? And what is the other one? The third diagram right here. I think you cannot see here the caption, but you will get it when I post the presentations. The third one is actually the same image taken from infrared radiation, right? From IR radiation, right? So that is how it looks like in the IR radiation. And you can see there are things that you cannot see in both these images, A and B, but only from IR radiation, right? So what you actually mainly see here is the dust, the glowing dust in the region. So these regions are very dusty. So there are large number of huge amount of dust in this region, and this is why they because that you have a lot of gas and dust in these regions, so they are kind of hotspot to the birth of new stars, right? So that's what you are seeing here. And what you need to understand here is how the sky looks like in three different wavelength regions. So this is why we need to observe uh, these different areas of the sky using different wavelengths to obtain a better understanding about what's happening in the universe, right? Right. So keep that in mind. So let's go back to the first instrument, which is the telescope, and see a little bit about the history of the telescopes. Now, these are actually two pre-telescopic observatories. So that is some of the monuments of ancient like uh, ancient creations that they used to observe the sky, right? So I'm not going to actually explain each by one. So they have basically used this kind of uh, structures to measure the positions of celestial objects, right? Mostly to keep track of the time and date, because in the ancient time they didn't have calendars, so they kept the track of time and date based on the observation of stars and other celestial objects on the sky, right? For this purpose, they have used this kind of different structures. So this is before we invented the telescope, right? Then what happens is in 1610, Galileo Galilei invented the telescope. That is the first ever telescope that we first ever telescope in the recorded history. And so he invented the telescope, and he used actually a small tube with lenses, right? So you know the small lenses that you use in the labs, right? So he used a tube and two lenses to observe the sky and gather more light than his eyes alone could. So he was very successful in this regard because he was able to capture more light, right, using this his smaller telescope. Now uh, he used these telescopes and observed for many nights, and so what he have observed from this telescope is revolutionized the ideas about the nature of planets and the position of the earth. right? So you all know his findings and everything. Now, if you come back to the modern age, so we have very large telescopes now already built, and these telescopes cost like hundreds of millions to billions of dollars, right? So these are like huge, very large projects, and cost a lot of money to build this huge telescope, right? And uh, before we look at these large telescopes and the technology behind those, let's just learn a very basic about the telescope, right? Now, the telescope has two basic functions. The number one is collect the faint light from astronomical source. So the main purpose of a telescope should be to collect light as much as possible, right? And the second one is focus the whole light into a point or an image, right? So that you have to collect the light and then you have to focus all the light to a certain point, right? So this is the two primary tasks that we should have from a telescope, right? I guess all of you know about this, right? But I need to make it very simple and very clear, because this is the first astronomy course that you are learning, right? So the two functions will be collect the faint light from an astronomical source and focus all the light into a point or an image. Now, the more light we can collect, the better we can study such objects. So that is like a rule of thumb for the telescopes. Right? So if you can collect more light, so if you can improve the telescopes in such a way that you can collect more and more light, so that will be helpful for us to study different kind of objects in a more better way, right? So that is uh, the advantage of developing the technology behind telescopes, right? So that's exactly what we have been doing. Right, now if when you take a telescope, so there should be a way to measure this amount, measure its ability to collect the light now. So I thought that the primary function of a telescope is to collect the light and then focus it, right? Now, to collect the light, we should have a way to measure it, right? And this measurement quantity is called as a light gathering power of a telescope. So each telescope has its own light gathering power, right? Which we can measure, right? So basically a telescope that collects these visible radiation or any other uh, light using a lens or a mirror, right? Remember that when we talk about telescopes, there are basically two types of telescopes. The first type, which Galileo invented, he used lenses, right, for the first telescope. But nowadays we have even mirrors in telescopes, right? And I will explain you a basic function of these two types of telescopes. And then the light gathering ability is basically determined by the area of this device acting as the light gathering bucket. So basically you have to calculate the area of this particular device which helps to capture the light. Now inside the telescope, there is a device that can capture this light, right? So what should be that device? That device is actually either a mirror or a lens, right? So those are the two basic, those are the basic elements of a telescope, right? So there are no telescopes without mirrors or lenses, right? If you have a lens, then it's a certain type of telescope. If you have mirrors, it's a different type of telescope. However, in both these telescopes, the primary function is to collect as much as light, right? Now the area of either this lens or the mirror will determine how much light that you can collect from that particular telescope, right? Now, if I give you an example, if the area increases, then the amount of light that it can collect will increase, right? Now you should understand why we are trying to build larger and larger telescope, because the larger the telescope, then you have more ability to collect more light, right? Now, if I take a telescope with mirrors, let's say you have a telescope with a mirror So the mirror is basically a circular shaped mirror which has a diameter of 4 meters. It can collect, and let's say you have another telescope with a mirror which has a diameter of 1 meter. Then actually, if you do a calculation, this 4-meter telescope is capable of gathering 16 times as much light as a telescope that has a 1 meter diameter. Basically, the larger the area, then you can collect more light, right? And this calculation is done using area of a circle, right? You know, the area of a circle can be given as 5d squared over 4, where d is the diameter, right? So that's why you have to divide it by 2, right? So that's how you collect the light, right? Now there is a question for you. What is the fraction of for more light gathered by 4-meter telescope compared to 1-meter telescope? Now, when I tell 4-meter telescope, so that means the diameter of that mirror using to make that telescope is 4 meter, right? When I tell 1-meter telescope, so that means the diameter of that particular uh, mirror that have used for that telescope is 1 meter, right? So that is the idea. So I guess you can answer this question now. So try to answer it. I think I have already discussed this. So I would like to see a few of you response to this one, and then we will go ahead after that, right? Right. I guess this is an easy question. So let me directly go to the answers. So all three who answered has the answer is 3 and 4. So I guess you can understand it, right? So it's a squared of the basically the diameter, right? So keep that in mind. So I'm going to close this one. Right. So I guess all of you can answer that question very easily, right? So that's basically you need to calculate the area, and we have done the same problem previously. So I mean, if you need to calculate in a proper way, this is how you do it, right? So you calculate the area of the 1-meter telescope and then the area of the 4-meter telescope, and then divided those two. But I think you don't have to do that, right? So it's not essential to do that, right? Right. And then the thing is, now let's see a little bit of optics behind this telescope. All of you have learned about the optics of telescope variable physics just to get things revised. So what basically lens is when you have parallel rays, they will be bent when it goes to the lens, especially to a convex lens, and so that they will come together in a single plane called as the focus, right? And this is where you will have this image, right? So that's how a lens works. And as I told you, there are different scopes. Now, if you take the remember that in this particular one, you have focus right here where you create the image right here, right? So the image will be created right here at the focus. Then there should be another people to look at this image. And that particular piece of equipment is called eyepiece, again, a part of this telescope. To view the image formed by the lens in a telescope, we use an additional lens, right? So that is called an eyepiece. And so you keep an eyepiece to look at this particular image created by a lens, right? Now, these telescopes that uses lenses have a specific name, and those are called refracting telescope, right? Now, these are the, I have seen that most people know about this kind of refracting telescopes. These are like this tube type of telescopes that we normally conventionally, when I tell the name telescope, everybody has an image about a telescope, and that image is actually about these refracting telescopes, right? I mean, that's how we are trained, and we have looked. We were told most of the time about these refracting telescopes, right? Currently, the largest refracting telescope is the 40-inch refractor at Yates Observatory in Wisconsin. So this is the largest one we have. Actually, the refracting telescopes, even we have this image in our mind about the telescope, always with the refracting telescope. Nowadays, the refracting telescopes are actually not that much popular, right? Most of the astronomical telescopes today, both professional and amateur telescopes, use mirrors rather than lenses to form an image. And these type of telescopes are called reflecting telescopes. And as the name suggests, you can see that these two types of telescopes are using two different mechanisms or two different properties of light. Lenses use the refraction from lenses, and the mirrors actually use the reflection from mirrors, right? And nowadays, if you look at in both smaller telescopes and larger telescopes, most of them are actually reflecting telescopes, right? But I have seen in Sri Lanka, which is astronomy is not that much popular. Still, most of you have this idea in your mind. When I tell a telescope, it should be always a refracting telescope, right? But it is not the case, because I can see that I usually get a lot of calls about purchasing new telescopes and how to select telescopes and those kind of things. So most of the time people ask about these refracting telescopes. However, the refractive telescopes are not that much popular in these days all over the world. It is mostly reflecting telescopes that are used in most of the places. For both amateur means the smaller type of telescope that we use in our day-to-day life, and also for the professional telescopes. Professional telescopes means these very large telescope that we use for research purposes, right? So these type of telescopes cannot be moved from one location to the other location. So these are huge telescopes. Right? Now, the first successful reflecting telescope was built by Isaac Newton in 1668. And after that, this reflector telescope is, they have reflector telescopes are developed so much. And the first image right here in the left-hand side is a refractive telescope, which uses lenses, right? You can clearly see that there is a lens right here, which we use to refract the light. And then there is an eyepiece, another lens right here as an eyepiece to keep your eye and look at that particular object. So this is a refractive telescope. And the reflector telescopes it looks like this, right? And so you have parallel rays, and then there is a mirror right here, and this mirror reflect the light, and then it go back to again to a secondary mirror right here, which all the light is collected in the secondary mirror, and then refocus it to an eyepiece. This is the general diagram, or in general how a reflector telescope works, right? And I think probably, let me try to show you one of these reflector telescopes, an actual one that I have. So let me see Just to take this one and show you how it actually works. I don't know whether you could see it. Let me. So this is actually one of the, these are called like amateur type of telescopes. Now you probably haven't, if you are not very much familiar, you probably have not seen telescopes like this. I don't know whether you can see it or not. So this is a reflector type telescope, right? Which is basically the second type, what you can see here on the right hand side, right? Now this telescope, now this is closed. I don't know whether you can see it. I can remove this cap from this side, and what you can see here is inside a mirror. I don't know whether you can see, there is a mirror right here at the, so let me, I think it's better to take it from the other side. So if I remove the cap, there is a large hole. I think you should be able to see there is a mirror somewhere right here, and that mirror is the one that you see in this diagram right here, a parabolic shaped mirror. So what that mirror does is that mirror reflects the light to a certain position right here around in this. So let me take it. So what happens is the mirror, this mirror reflects the light, and there is a secondary mirror somewhere here inside this tube, and that mirror is angled to a 45 degrees in that way, and that it will reflect the light from that secondary mirror, and it will go through this direction. Yeah, you can keep the eye right here, and there is an eyepiece to look at it. I'm not sure whether it's clear or not, right? So there is a place that you can keep the eyepiece and look at that particular object. So this is a basic, so I just need to show you to give you an idea. This is a basic reflector type mirror, and the size of the mirror that you have in this telescope is actually 4 inch, right? So that means the diameter of the mirror is just 4 inch, right? Right. So that's just to give you an idea how a telescope, a smaller telescope, actually looks like. Because I have seen, noticed that most of you have seen these refractor type of tube type telescopes, but most of you may not have familiar with this reflector type telescopes, right? Right. Now in reflector type telescopes, you have a concave mirror and is placed at the bottom of the tube of open framework. So that's what I have seen here. There is a tube. You probably have seen it now. And you have kept a mirror at the bottom of the tube. And then this mirror reflects all the light back up to the tube. Right? So which means it will reflect back again towards the same side where the light entered to this tube. And then there is a place which is the focusing point of the mirror. There is a second mirror, which we called as a secondary mirror. So that mirror is very smaller, and it is angled to a certain angle. Typically, it's 45 degrees angled. And this image is go to 45 degrees angle, and this is actually called, then you reflect the light from the secondary mirror, and all the things will be focused, and you will be looking at that through eyes, right? Using an eyepiece. So that's how, in general, these smaller telescopes work, right? And this place where where this all the light get focused from the primary mirror, because this first larger mirror that you have at the end of this tube is called the primary mirror of a telescope, and the focus, the place that all the light is focused by that primary mirror is called the prime focus, right? So these are specific names, right? And it is, so we will keep this angled smaller secondary mirror on this prime focus, right? So then it will reflect back all the light again towards the eyepiece where you can keep your eye and see it, right? However, there are other ways of looking at these images formed in the primary focus. We can actually have this additional mirror, which we called as secondary mirror, or we can have some kind of detector in that particular position, right? Now, most large telescopes are actually, when professionals are using telescopes, these telescopes are actually Cassegrain focus telescopes, right? So it's a different one. Basically, it has a mirror, but what it does is once the light is reflected from a secondary mirror, it has a smaller hole in the primary mirror that the light will go through that hole in the primary mirror, and you are observing below the telescope, right? So let me see whether there is a diagram, then it will be easier, right? Basically, for the reflector telescopes, there are, you can see that there are three different types, right? And in these three diagrams, I have shown you three different types, right? And so this one is called prime focus. So which means you have the primary mirror right here, and it will be focused to a point right here, and you have to have some kind of detector here to look at the image. And this type is called prime focus, right? And then this one right here, you have the mirror, right, large mirror right here. All the light is collected to this place where you had the prime focus right here. But now you have a secondary mirror angle, which you can again reflect the light, and you can keep the eye somewhere here to look at the object that you are looking at. And this is called Newtonian focus, right? And the telescope that I have just shown you, which I have here, is a Newtonian focus telescope. And the third type that I told you, Cassegrain focus, is once again you have the primary mirror right here. The only thing is there is a small hole in the primary mirror right here. You can see the mirror is not complete. There's a smaller hole here. And the primary mirror, you get all the lights get collected right here for the secondary mirror, and then reflected back again towards the same side where you have the primary mirror, and then you have a smaller hole here for all the light to go through that particular hole, right? So this is called Cassegrain focus, and most of these professional type telescopes are built in that way, right? Right. Now you can see that I have talked basically about two different types of telescopes now, right? That is reflector telescopes and refractor telescopes. And you can see that I have talked a little bit more about reflector telescopes and introduced there are three types of focusing mechanisms for the reflector telescopes. And then now you should have a question in your mind, right? That is, now we have two types of telescope, reflecting telescopes and refracting telescopes. They basically perform the same function, because it doesn't matter which telescope that you are using, as long as you can see the same object from that, right? But when you look at, I have also talked a little bit more about reflector telescopes, and if you look at all these large modern day telescopes, almost all these telescopes are actually reflector telescopes rather than refractors. There should be a reason for that, right? For that to happen. Anybody have any idea about what may be the reason for that? That you have, more of reflecting telescopes rather than refracting telescopes, right? The reason is actually there are different reasons for that. One reason is the amount of refraction that light undergoes depend on its color, and all of you know about this from optics, right? If you take the blue light and the red light, the amount of refraction that they have depend on their color. The red light will bend, refract in a different way than the blue light, right? Now, as a result of that, now this particular effect is called a chromatic aberration. And as a result of this particular effect, this will blur the object's color image, right? For example, let's say you are looking at a star, and all of you know that if it emits visible light, and if you are look through a refracting telescope, then what will happen is, uh, you know that this particular visible light has 7 different colors, and they will bend in a different way through the lens, right? So which means if they bend different amount, then what will happen is the image that you are going to observe will be blurred, right? Even though if it focus on a particular point, because of these different wavelengths focus at different points, the image looks like blurry, right? So that's what will happen, and this particular effect is called chromatic aberration, right? And also another problem with the lenses is the lens itself absorbs some of this light passing through it, right? And that is another problem. And the other problem is, now in the when this first telescope was invented by Galileo Galilei, he was building these smaller telescopes, right? And because of that, he used smaller lenses. But when it comes to the modern day, we are like, making these huge telescopes, 1 meter, 2 meter, even we have 8 meter, 30-meter telescopes now. That means the diameter of this mirror is 30 meters, right? So I will show you those kind of, some of the pictures of those kind of large telescopes. Now, what happens is when the telescopes becomes larger and larger, you have to, if you are going to make it from lenses, you have to make these huge lenses, right? Now the problem with the lenses is you cannot make these huge lenses, because then the lens will be very heavy, and it will be difficult to evenly support these large lenses from its edges, right? Because the edges are very thin of a lens, and if you try to support it from the edges, because of this weight, the lens will start to sag and deform, right? So that is another problem with the lenses. And you can see that these refracting telescopes have several issues, right? Right. Now, apart from this, actually, I would like to add something here, which is not mentioned here, which is a practical thing. The bang for the bucks. So this is means, how would you say this in a proper? This is like the amount of the money that you pay for a telescope depend on its size. Normally, what happens is the price of telescope will go higher when the light gathering ability is larger, right? So that means if you have a telescope with larger diameter, then you have to pay more money, right? Now, when you compare the amount of money that you have to pay for a reflector and refracting telescope, it is reflecting telescopes are always cheaper, right? So that is something that is not in the textbook, but I mean, it's something practically true, right? Reflecting telescopes are always cheaper to buy, right? And so I have added here a slide that will help you. For some reason, let me see, this slide is a little bit, the words are going off. I think this is due to the platform, the changes in the platform that I am using, but I will just explain you this. If you are going to choose your own telescope, I don't know how many of you have a telescope with you. I mean, telescopes are very expensive in Sri Lanka, right? And even it's hard for us to buy it, right? But I may have a good news for all of you, because we have a project here in the University of Laguna that we started like 4 or 5 years ago to build telescopes, right? And it seems to be becoming success now. So hopefully we will be able to, have some telescopes from us in the market, so that you can buy it probably for a little bit of affordable price. But I mean, price, I don't know still, so we are still developing it. Right now, if you are going to buy a telescope from the market, you need to do some research, of course, right? To find the best models you need, right? So there are different, branded names in the telescope market, which I do not want to, mention the names here. But the factors that you should think when you are buying a telescope is depend upon your preferences, right? The one thing is whether you are going to setting up this particular telescope in one place and leave it there, or do you want this instrument to as portable one, right? Where you can take it to different places, right? Now, one important factor for a telescope for sure is how portable that particular instrument should be, right? Now, if it is to be portable, it has to be smaller in size and less weight, right? So this is one of the huge practical problems when you are using a telescope. I mean, the people want to look at galaxies and those kind of objects that are very far away from us. But if you are need to get a good view of these deep sky objects, your telescope should be larger. When you have a larger telescope, then problem is the price is higher and the size becomes larger. And at the same time, the weight is also a problem, right? Now, if you can take a smaller telescope, then what will happen is it will be the telescope that I have shown you is just a 4-inch smaller telescope. But the advantage is it's lightweight. You can take it to anywhere with you, right? So things that you have to consider is whether you are going to take photographs with the telescope. Then if you are taking photograph, then you need to have a good mount, right, for the telescope. That you can track these objects with the movements of the Earth's rotation. And the other thing is what kind of objects that you need to observe, right? If you need to look at just star clusters, comets, planets, and galaxies, so you need to observe all kinds of celestial sights, right? So depending on what you need to look at, and then your preference will be different, right? And also the price will be also a factor, right? Right. Basically, there are key characteristics of a telescope. One is the aperture size. How large is the telescope should be. The larger the aperture, more light you can gather, and fainter the objects you can see, as you know. And as there is this point that I have mentioned, your telescopes of a given aperture that uses lenses are typically more expensive than those using mirrors, right? So this is something that the in general public do not understand, because when you say a telescope, you always have you in your mind that looks like a tube kind of thing, right? Not the one that I showed you, but it is always cheaper and better to go for these reflector type of telescopes that uses mirror. So that's always cheap and it's easy to handle as well, right? And also the telescope mount is one of the more important factors as well, depending on what you are going to do with telescope. And the other thing is, the last one is the telescope requires some practice to set up and use effectively, right? And don't expect everything to go perfectly on your first try. I mean, these are, the real situation about the telescope, which I want to explain, because people used to think that, okay, you go and buy a telescope and you come home and you can observe anything in the world that you can, right? So that is not going to happen, because telescope, once you bring it, you need to focus it. And so there are a lot of elements. I can give you like, hours of lecture about setting a telescope and how to use it, but I guess this is not the time. But these things are actually some of the practical things that, I mean, it's better that you know about these things, right? As students who learn astronomy, how to things about the telescopes, right? I guess that the best way to use a smaller telescope is once you bring it, make sure that you align and focus it in the daytime and prepare it for use it in the. So there is something called uh, this piece. I can't remember the name of that. The viewfinder. So you have to focus everything using electronic viewfinder or laser, whatever the viewfinder that you have in a telescope, right? And then you prepare everything before the night comes, and then you start using it for observations. Right. So that's about the practical things that you have to you need to know about the telescopes. And here is an image of a large telescope mirror. Now, in nowadays, the telescope industry is a completely different one. It has developed so much that you make very large mirrors, such as this one right here on your screen. Right now, this image shows this is a primary mirror of the European Southern Observatory, very large telescope. Right. So if you type the name VLT telescope in the internet, you will get the information. This is a primary mirror that they are preparing for this VLT telescope, or what they have in this telescope, right? And this mirror is little over 8 meters in diameter. Think about a mirror that has a diameter of 8 meters, right? So these are the telescopes are this much huge in nowadays, right? I remember that the one that I have used is one was the 1 meter telescope I used around 2018, which was in Kitt Peak, Arizona. And the second telescope, the one that mostly I used was a 4 meter telescope. So that means the area or the diameter of the primary mirror is 4 meters, right? Now, reflecting telescopes have grown even larger. So in 1948, US astronomers built telescope with 5 meter diameter, right? On Palomar Mountains in South California. And now we have there are telescopes with primary mirror diameter of 8 to 10 meters. So these are huge telescopes, right? There are actually new technologies now designed to work well even in the infrared region, right? Not only in the visible light for telescopes. Right now, here is two images. The first one is Palomar 5 meter telescope. This is also called Hale telescope, which has a very complex mounting structure and to telescope to swing easily into any position. On the left hand side, you have this 5 meter large Palomar telescope, and at the same time, what you have in this right hand side is the Gemini North 8 meter telescope. So that is, as I told you, when I tell 8 meter telescope, that means the diameter of the primary mirror of the telescope is 8 meter, right? But if you look at the two images and compare it, what I want you to understand here is the image in the B section. There is a very large 8 meter diameter, which is a telescope that has a lot of capabilities compared to this older 5 meter telescope, right? However, if you look at these two structures, you can see that one in the right hand side is less massive. The whole instrument seems to be smaller than one in the left hand side, right? And this is what the development of technology can do you, right? So you can get more capabilities with a simple structure nowadays. Right, so here is a list of telescopes that are being built nowadays. And this the first one is European extremely large telescope, and diameter of the primary mirror is 39 meters. And you can see how large it could be once it is finished, right? So this is estimated to have first light detected in 2025. So which means they are still working on this. And then there is 30 meter telescope, Mount Keohai, Hawaii, right? So they have This is again a 30-meter telescope, again planned to have finished in 2025. And then you have the giant Magellan telescope in Chile, which is again a 24-meter telescope. All these three telescopes are to come in near future, right? So you can see that if you will become an astronomer in the future, you have a lot of work to do, because these telescopes will produce, some unprecedented huge volume of data in terms of images and spectrums and all kind of things that you will have to analyze as astronomers to find, completely new things in the universe. Like that, I have mentioned, maybe 10 to 12 telescopes here, and all of them are larger than 6 meters, right? Now, I told you that the one that I used when I was doing my research was like a 4-meter telescope. It was one of the largest 10 telescopes in 70s, right? You can see how the technology has developed now with that particular telescope, not even in this list now. Right, so just to give you some idea, this is the 36. This is a 10-meter Keck telescope. This is basically composed of 36 hexagonal sections. When these telescopes get larger and larger, the new technology is that you don't make one single mirror. Instead of that, you are making this hexagonal structured and connect all these things together, right? That is how it works. And right now, there is we talked about the telescopes and how it works, different types of telescopes, how a smaller type of telescope works. And we talked that there are two different types of refracting and reflecting telescopes. And then I have introduced you some of the very large telescopes in the optical regions. Now, some of them are still in the development phases, and some of them are, we are already using it, and you can see that how large these telescopes are. And at the same time, it should come into your mind that how much money that we are using, spending for this. And this is like $1 billion industry, right? If you have to build these large telescopes, takes billions of dollars, right? Now, let's say you in Sri Lanka, you select a location and build one of these large telescopes, right? I mean, this is not going to happen, right? So I'm just imagine, right? And you spend, let's say, billions of dollars, and somehow you have managed to find a sponsor for you to build a telescope, right? Do you think that he will straight away come and build a telescope here, spending money, even if you give a land and everything to him? I mean, not smaller telescopes, these very large telescope, right? Now that is not going to happen, right? Because if, for example, if you think about spending money to build a telescope in an area like where I am living, it's always raining in this region, right? I mean, if you have rains and clouds in most of the days, and if the sky is not clear, then it doesn't matter how many $1 billion that you have and how many $1 billion that you can spend to make a telescope, because you are not going to observe anything out of that from an optical telescope, right? That is because the weather factor, right? So you can see that there is a limit for this one, that is which is something that we cannot control, right? So this is why I used to tell this section, the performance of a telescope is determined not only by the size of its mirror, but also by its location. So it is, the size is important, but it is also important that where you are going to locate that telescope, right? Now, when I tell these names of the telescopes and locations, you probably have seen that most of the time there are only few locations that we are talking about, right? So one location is Keck Mountains in Hawaii, USA, and then there is Kitt Peak National Observatory in Tucson, Arizona, and I was working there for a few years. When I say few years, that means few observing sessions during those years, there are specific sites, right? And when I show you the images for these optical telescopes, you will see that most of them are in the mountains, right? And also in dry areas where you do not have much rain, and also you should have less humidity, right? And we will see what kind of conditions that you should consider if you want to locate one of these large telescopes, right? Otherwise, it will be a waste of money, right? Now, the most obvious limitation is weather that I have talked, right? For example, clouds, wind, and rain, right? Now, at the best sites, the weather is clear as much as 70% of the time. So that is something that you are looking at if you want to build one of these professional telescopes, right? You just do not go straight away and build a telescope somewhere. You need to do a good study about the weather conditions, right? And then look at how many clear days you have on average. Now, normally we expect to make the money worth that you are spending for a telescope is at least you should have around, 75% of the time clear nights during an year, right? That means if you take 100 days, at least you should have like 75 days of clear nights, right? Otherwise, there is no, use of having a telescope, right? And now the problem is even on a clear night, there is the atmosphere filters out certain amount of starlight, especially in IR, where the absorption is due to primarily to water vapor, right? As astronomers therefore prefer dry sites generally found at high altitudes. So the other problem is even the night is clear, the atmosphere used to filter out certain amount of light from the stars, right? And especially this is true for IR region, infrared region, right? Because IR is absorbed by water vapor, right? Due to primarily this water vapor. And because of that, when astronomers looking to build a telescope, they always prefer dry sites, which are generally found in at high altitude. So this is one why astronomers are interested in building these large optical telescopes in mountains, because mountains are the places where you have high altitude, which you can avoid most of these absorption issues, and also you get clear skies, right? And number three is, of course, the sky above the telescope should be dark, right? So near cities, the air scatters the glare from light, producing illuminations that hides the faintest stars. So that is another big problem that we have when you are building telescopes, right? For example, let's say somebody has money and he need to build a telescope in Colombo. So you go to Colombo and try to build up a very large telescope, right? Now that's, I have seen sometimes this happens in Sri Lanka as well, but that is not going to work, right? Even though you have all the money in the world to build a telescope, if you are going to build it in a large city like that, you are actually uh, not optimizing your telescope, because most of the time you will get light pollutions and you won't be able to see most of the things because of the glare coming out from these street lights. Now, I can give you an example because I worked here in the Tucson Kipik National Laboratory. So they have a city which is around 75 kilometers away from this observing site in the mountain. The city is called Tucson, and they have special laws and regulations for using street lights in that particular city due to this observatory that they have nearby. So nobody can, put up lights as they like. So there are certain conditions that light has to, directed towards the earth, and those kind of regulations, right? To avoid this light pollution that will be affecting for these large cities. Uh, normally the recommendation is that you should actually locate your telescope at least 100 miles from the nearest large city. Right? That's how normally it's a standard. And the fourth requirement is that the air has to be steady, right? Otherwise, what will happen is when light passing through this turbulent air, then what will happen is you will get a blurred image. So the image is not will not be sharp, right? And astronomers have a specific name for that. So that is called bad seeing condition, right? I mean, this word is, maybe looks a little bit weird for you, but this is a term that astronomers basically use. Once you go for a telescope observation and once you take an image, if you see that all the images are blurred, even after making the focusing and everything correct, astronomers used to tell that we have a bad seeing today. So that means there are a lot of turbulences in the air on that particular day, which means, so this is why the images get blurred, right? And sometimes astronomers used to tell that, okay, today we have a good seeing condition. So that means the environment is, or uh, the air is calm. So you have not that much turbulences in the air. And because of that, you can easily get clear images, right? Right. So here are some examples to have these telescopes, and you can see this is one of the examples, and this is somewhere called Chile, Atacama Desert, where you have this VLT telescope, which is an 8-meter one, and you can see they have different sites to place these telescopes. Right? These kind of areas where you have light pollution and clear skies, those kind of things. Right. Right. I think anybody have any questions up to here? Any questions? Right. So if you actually do not have questions, I would like to uh, probably, I thought that this is probably a good place to stop the lecture. And so we have been talking about the telescopes basically. And there is one uh, right. So there is another section that I have to talk about this resolving power of a telescope and everything. And then about the detectors before we go into the next section. So on the next day, I will start, talking about these resolving power of a telescope. Once again, this is a concept that you have already learned in physics, the resolving power. But here, what I am trying to teach you or trying to discuss with you is how this particular concept about the resolving power is important to in telescopes, right? In our observations, how it is affecting for our observation. You will see that uh, what is the use of some of these concepts that you have learned in physics, right? And so since it's a completely new section, I am going to stop from here. And most probably I will take on lectures again from tomorrow morning, right? To finish up this section. And just to give you some details, so for your in-class examination, I have a plan to have it, let's say from 2 weeks from now, between somewhere a date between 20th and 30th July. Right? So I will talk with your department and decide the date. And the things that you will have in that particular exam will depend on how far we go with the lectures, right? So most probably there will be few other coming sections included in that particular uh, uh, lesson, right? Sorry, and in the particular exam, right? Now, for now, I'm going to stop from here. So I will take on uh, having the lectures. So I will take on from this particular position. And once we finish this particular part, I think I'm sure that I can finish it on the next day. Then we will go on to talk about the planets and the stars, right? So that will be the next section. And the third section of the lectures will be galaxies and galaxy clusters. So I will have probably 5 or 6 lectures about galaxies, galaxy clusters, and cosmology, and maybe 7 to 8 lectures about the stars, different type of stars and evolution of the stars, those kind of things. And then probably next 3 or 4 sections, probably next 3, let's say 3 or 4 lectures will be about, I mean 3 or 4 hours will be about our solar system and the planets, right? Planets, and maybe about the sun as well, right? And sometimes I may take the stars to begin, and then later we may move on to the planets, and that will depend on how it works, right? Right. So if you do not have